Let's begin our next chapter's lessons. Chapter 3, are acids and bases. It's really our first introduction to reaction mechanisms in organic chemistry. Reaction mechanisms are those pathways that reactants take to become products. The mechanisms are often multi-steps and involve intermediates. Many steps in organic chemistry involve acid-base reactions. So as we get introduced to the process of predicting products based on reaction mechanisms, it's an important first step to understand acid-base chemistry so that we can utilize that knowledge to be able to predict the products and how the reactants obtain their product form. So in our chapter, we're going to consider rules that show how to classify reactive groups. Remember that functional groups that we just came off of from chapter 2? Let's look at those functional groups within these molecules from the standpoint of which ones will act as acids and which one will act as bases, and how we can track the flow of electrons from electron-rich to electron-poor domains. The step-by-step processes of the chemical reaction will then be used to codify those processes into very few, specific, easy-to-understand types. The heart of this chapter is tracking electron flow from electron-rich to electron-deficient domains to predict the outcomes of acid-base reactions. So many of these reactions that occur in OChem are either acidic and base reactions, or they'll involve a process of acid-base in some part of the reaction mechanism. And so we need to really understand the simple fundamental reactions that will enable you to just see how chemists used curved arrows to represent these mechanisms. The curved arrows, which was introduced in the earlier lessons from Chapter 1 and Chapter 2, allow us to track electron transfer. I'm going to begin with a review from General Chemistry acid-base theories. This acid-base theory was presented at USM's Chemistry 107 course. It's called the Bronsted Lowry acid-base theory. So in my mind, you've had exposure to this, and this is a review. Let's dive into the theory that tracks proton transfer. When you think of Bronsted Lowry, you think of proton transfer. And a proton is nothing more than a hydrogen ion, H+. The Bronsted Lowry acid-base reactions involve the transfer of protons. We define a Bronsted Lowry acid as anything that can donate a proton. When I say proton, you think hydrogen ion. And a Bronsted Lowry base is any substance that can accept a proton. A hydrogen ion acceptor is a base. A hydrogen ion donor is the acid. In Bronsted Lowry, it's all about proton transfer. I make that distinction because in a moment we're changing theories and we'll be tracking electrons in the Lewis theory. Bronsted Lowry, always keep in mind that it's proton transfer. And when we think of protons, it's just simply tracking the placement of the hydrogen ion. In a first reaction, we see a water molecule, H2O, reacting with HCl. In this acid-base reaction, we see using our electron arrows that the oxygen on the water molecule is a very electron-rich domain. The negative regions on the oxygen make this highly negative, and of course the hydrogens then are left as positive in terms of a polar molecule. Water is very polar, it sets up hydrogen bonds. We can see that this particular bond is very polar as well, creating a very strong electron deficiency on the hydrogen ion and a very negative region on the chloride ion, just based on the polarity and electronegativity difference in that bond. So we would call this oxygen electron rich and the hydrogen electron poor. I tend to use the word electron deficient. The electron deficient hydrogen is the target then for this electron-rich area on the water. And notice that when I follow the arrow, I go from rich to deficient electron area. And that's going to form the new bond, creating what's called the hydronium ion. Hydronium is a protonated water molecule, H3O+, leaving the electrons that were in this bond to collapse back onto the chloride ion. And now we see that there's 8 dots around it, chloride, Cl negative. In this particular example, what did we see? We see a conjugate pair. HCl and Cl negative are different by just one hydrogen ion. These are known as conjugate pairs. H2O and H3O positive are known as conjugate pairs. We see a proton has been transferred. The substance HCl would be known as the acid, the Bronsted Lowry acid. It has the ability to donate a proton. The resulting species after the transfer is known as its conjugate base. One less proton, the resulting species on the product side is its conjugate base. Water had the ability to accept a proton. By definition, it's labeled as the base, the proton acceptor. The species that forms on the product side after it has accepted the proton is known as its conjugate acid. The conjugates are the resulting species after the proton has been transferred. If you have a base, you know the other must be its conjugate acid. Here we have an acid, therefore you know the other label has to be its conjugate base. So just check in with the following vocabulary terms. Can you define the term acid, base, conjugate acid, and conjugate base using the Bronsted Lowry acid-base theory? Vocabulary check. We know that an acid has the ability to donate a proton. The species that forms after it has accepted is known as its conjugate base. So that forms after receiving the proton from its acid. An acid is a proton donor. It didn't receive. I said that back. Let's write this different. I'm so sorry. I want to say it more clearly because an acid always has one more hydrogen. Than its conjugate base. Let's just put that in parentheses to emphasize these definitions. The conjugate base is the species that results after the acid has transferred its proton. A base is a proton acceptor. And conjugate acid, again, would have one more hydrogen because the acid is always hydrogen-rich compared to the base. It's a species that results after it's accepted the proton. So, again, it's the species that results on the product side is what I'm referring to, that acid base are always on the left side of the arrow, conjugates are always on the right side of the arrow. So this is the species that results after the proton has been accepted. So we always look for these pairs in the Bronsted Lowry acid-base theory. An acid plus base will always equal a conjugate base plus a conjugate acid, just to think about the partnering. An acid produces a conjugate base. A base produces a conjugate acid. And what we're doing is moving a proton from one species to the next. A proton is a hydrogen ion. So if we think about just simple practices, we know that the conjugate acid has one more proton, and protons are positive. Let's suppose we have HSO4 -1 as a base. This is the hydrogen sulfate polyatomic ion. To form its conjugate acid, we add a proton. We add one more hydrogen ion. So instead of just one hydrogen, it now has two hydrogens. It went from a -1 charge to no charge. Now remember on a number line, if this is 0, -1, -2, 1, 2, we're starting here on the number line with HSO4 negative. Adding a proton makes it become one more positive. So if I'm standing here and I become one more positive, I went to neutral, H2SO4, no charge. If I stand here, HPO4, 2 negative, I'm standing here at the number line, I add one more proton. Adding one more proton instead of H1, it's H2PO4, but adding a proton made it go from a -2, one more positive, to a -1 overall charge. Hydrogen phosphate polyatomic ion became dihydrogen phosphate polyatomic ion. And your last one is ammonia, NH3. Notice that it starts at a 0 overall. And if I'm starting at a 0 and I become one more positive by adding a proton, you form NH4 +1 overall charge. Adding a proton makes it one more positive on the number line. Ammonia is NH3. We can see that it has room to accept a proton based on this rich area of electrons here. And what forms then is its polyatomic ion known as ammonium, NH4. Now, with that extra positive hydrogen, it carries the +1 charge overall. If you see a pair of acid-base chemistry, think Bronsted Lowry, because we have two reactants forming two different products, and you can see that they're always related by the difference of one hydrogen ion. So when you see, for instance, H2Y -1 forming H3Y, we know that those are conjugate pairs because they only differ by a hydrogen ion. The one with more hydrogen ion is always the acid. The one with less hydrogen ion is always the base. Now notice they only give us acid-base here, so in my sapling, I would have to put that this is an acid, but by definition, it's technically called a conjugate acid. Between H2Z negative and HZ2 negative, H2Z negative, HZ2 negative, that sounds so similar, but they're different by just one hydrogen ion. The one with more hydrogen is always the acid. The one with one less hydrogen is always the base. And again, in sapling, you'll have to just type in base there, click and drag, because there's no conjugate choices. Conjugates only differ by a hydrogen ion. I'm reviewing with you the 7 strong acids, and I ask you to memorize them. By memorizing them, you're doing yourself a favor because you've also then memorized all of the weak acids. The word strong means that it 100% dissociates when placed in water. It is a strong electrolyte. It does not set up an equilibrium, but rather a complete push to the right. When HCl is placed into water, 100% of the hydrogen dissociates from the chloride, And what we set up here is conjugate pairs, H3O plus called hydronium, and Cl negative called chloride. HCl and Cl negative are conjugate pairs. Water and hydronium are conjugate pairs. 100% pushes to the right, forming hydronium ions. They're called strong. If they're weak, they only partially ionize. Hydrobromic acid, HBr. Hydroiodic acid, HI. We have hydrochloric, hydrobromic, hydroiodic. Those are binary acids. By binary, I mean it's just hydrogen hooked to a halogen, binary. Then we start seeing oxy acids, which involve polyatomic ions. Chloric acid comes from the polyatomic ion chlorate, making it an acid, HClO3, chloric acid. Perchloric acid comes from the polyatomic ion chlorate, perchloric acid, HClO4. Nitric acid comes from the polyatomic ion nitrate, and sulfuric acid is the diprotic acid, H2SO4, has the two hydrogens, H2SO4. Memorize these 7 strong acids, and you'll now know all the weak ones as well. I made you do this in Chemistry 107 if you had me back then for Gen Chem 2. So we're seeing that once we have those 7 acids memorized, everything else is a weak acid, and by weak we set up an equilibrium arrow through the dissociation. Let me emphasize sulfuric acid as a strong acid. When I place that into water, it ionizes 100%, but it only releases 1 proton at a time. So H2SO4 releases 1 proton 100% of the time. I have to transfer that to water. So I'm going to write hydronium and leaves you HSO4 -1. I'm going to repeat. In Bronsted Lowry, we only release 1 proton at a time. So it's a stepwise ionization. Notice the conjugate pairs can only differ by 1 hydrogen. This was said to be strong, 100% releasing just 1. In the next ionization, HSO4 negative ion, when it starts to dissociate, it is not one of the 7 strong acids. It is not the one that we memorize. It's very different than its parent acid, H2SO4, which means that it struggles to release that second proton. And when I say that, I'm showing it with double arrows, that a little bit will push to the right, but the vast majority of this equilibrium indeed lies to the left side. So we're showing a weak electrolyte, a weak in terms of the ability to ionize, and this set up the entire thing we called a Ka constant, a number. The magnitude of the number is what's interesting to a chemist to give us an idea of how strong or how weak the acid is. A Ka is called the acid dissociation constant. Bringing back some Gen Chem 2 content here. Acids and bases exist only in water. We must have an ability to transfer protons, and we have to have that aqueous medium for that to occur. So hydronium is the strongest acid that can exist in water to any significant extent. Anything stronger is just simply going to transfer its proton to a water molecule to make hydronium. HCl is a strong acid. HCl does not exist in water. We wouldn't find the molecular compound HCl where H is bonded to Cl. It does not exist in water. What it's reminding us is, if indeed HCl is strong, and it is, it's not going to keep the hydrogen on the chlorine. It's going to transfer its hydrogen to the water to create the hydronium ion. So this is the strongest acid that actually exists in water. If you have a stronger acid, it's going to let go of its H to make hydronium. Same story here, but for hydroxide. OH negative is the strongest base that can exist in water to any significant extent, because any base that's stronger than hydroxide will remove a proton from water to make hydroxide. So by definition, H3O plus in water makes it acidic. OH negative in water creates a basic solution on our pH scale. Remember a familiar format from a double replacement reaction that we learned back in general chemistry. A double replacement reaction says, let's take a compound called AB and react it with a compound called CD, and you'll create new compounds based on exchanging the two positive ions. A we know is positive, B we know is negative, because when we write formulas, positives are always written first. C is positive, D is negative. These two positive ions simply exchange places. A will go to D based on charge. C will go to B based on charge. Now, if this happens to be an acid reacting with a base, always we can predict the formation of a salt and water. Let's take a look at an example of that pattern. Acid plus base creates salt plus water. HCl is hydrochloric acid. H is a +1, Cl is a -1. Sodium hydroxide, Na is a +1, OH is a -1. We have an acid, starts with an H, reacting with a base, ending with an OH. Based on the pattern called double displacement, H goes to OH, H2O is molecular water, and Na goes to Cl. Based on charge, we get NaCl. An acid plus a base formed salt and water. HCl is a strong electrolyte. It 100% dissociates in water. Sodium hydroxide is a strong electrolyte. It 100% dissociates in water. Water is a molecular compound. It is a non-electrolyte. Leave it together. And sodium chloride is a salt. It is a strong electrolyte. Therefore, we know it dissociates in water. So just reviewing the concept of strong electrolytes. They don't exist in a water medium as in a bonded form. They have dissociated to form their aqueous ions. That's the definition of electrolyte. So remember that chloride and the sodium remain unchanged. We had a term for that. They're called spectator ions. To write the net ionic equation, we eliminate those spectators and simply write the actual chemical change where hydrogen and hydroxide combine to form water. And we realize that hydrogen ion does not exist in water. It's always a form of protonated water. So you'd really have to combine two waters to form hydronium and hydroxide. When I see hydrogen ion written on a piece of paper, my mind automatically knows that I'm truly referring to hydronium, the protonated version of water. A free-floating proton just can't exist in water. It'll always attach itself based on charge. So this is what we've shown, the sodium ion and the chloride ions being eliminated because they are spectators, and we show the formation of water molecules. So hydronium, H3O+, reacts with hydroxide, OH negative, forming water. An acid-base neutralization. I pulled this one from an old test question, and I just pulled it here just kind of as a practice before we change gears and talk about Lewis. It's Bronsted Lowry theory. So, which of the following is not a conjugate acid, conjugate base pairing? And notice it says in that order. So I've got a list. What's written first is acid, and what's written last are the bases. Which one of these do not follow the correct form? And just really quick to decide, remember this general rule. Acids have one more proton than a base. Which one of them has more hydrogen? Which one has less? That's what we're trying to decide. H3PO4, H2PO4 negative. Yeah, the acid has more hydrogen. That's good. Here is the same in letter B. The first one has more hydrogen. That follows the definition. Notice here, this is the acidic proton. It's been removed. Here is the hydrogen that's been removed. But all of a sudden, I see in letter E, the wrong form. The acid has to have more hydrogens than the base. It does not in this case. In this case, the second one would be labeled the acid. The first would be the base. Therefore, it's not written in the correct order. So when you're staring at these kind of questions, just make it a little bit easier and reword the question to simply ask yourself, which one has more hydrogen is always the acid, and try to find the one that's standing out as different as compared to all of the others. Here's another test question. It says, let's find the Bronsted Lowry bases in the following equation. And I know it's Bronsted Lowry because I'm looking at conjugate pairs. Conjugates are always different by one hydrogen ion. Phosphate and hydrogen phosphate are conjugate pairs. Water and hydroxide are conjugate pairs. Conjugates differ by one hydrogen ion. We want to know the bases. The bases have one less proton. Between PO4 3 negative and HPO4 2 negative, the first has one less hydrogen. It's the base. Between hydroxide and water, hydroxide is the one with one less hydrogen, so therefore it's the base. One less proton makes a base. So we're looking for phosphate and hydroxide. You can also quickly eliminate conjugate pairs because one has to be an acid, the other must be a base. So those make no sense. And so we're able to kind of figure out letter B just by kind of diagramming conjugate acid-base pairs. The second section of your chapter is a review from something we've already emphasized in earlier lessons, and it's how to use curved arrows in illustrating reactions. Let's pause here and just let this video digest, and when ready, start up with your second section.